Look at that, Dion. Beautiful downtown Hollywood.
Great view.
Southern California. Good to see you.
Great to see you there.
Yeah.
Yep.
So, Dion, wanted to talk to you about what you're doing in the wafer scale and the heterogeneous design philosophy that you're using right now to get things done.
Sure. Yes, we are pushing the boundary of monolithic integration by doing actually functional disintegration and taking IP at the level of a chiplet. So instead of taking IP blocks as part of an SoC, we kind of functionally disintegrate that SoC to some level and then put a boundary around the whole chiplet that is built with just like a chip technology. So we take the boundary of the chiplet, and that chiplet is then integrated on a wafer scale package. So we are scaling the package. Chip technology has scaled greatly, but package hasn't scaled. And now we are really bringing that opportunity to scale the package and extend Moore's law into this heterogeneous space where we can mix and match different technologies to build rapidly functional systems. So if you have enough chiplets to serve different functions and they have some level of signaling protocol that they agree on, you can then rapidly create useful engineered systems at the package level. And then the idea is you take these chiplets and you put them close to each other, about 100 microns apart or so, and run simple parallel wires between these chiplets. And that's the effort that is going on at the UCLA Chip Center with my colleague Subbu Iyer to really see how can we bring this heterogeneous system integration that would allow us to rapidly prototype big systems with wafer scale packaging.
Well, and let me try to understand this a little bit, because we're talking about an 8-inch wafer.
We're talking 8-inch, maybe 4-inch to start, but then going full scale. So we have now a project called Derby, which is for emulation of a large number of radar systems, real time, short latency, very high external I/O bandwidth, and a lot of compute. We're talking about 300 millimeter wafers, which if you take a square of that, it's about 200 by 200 millimeters, or 40,000 square millimeters of silicon. And this is then extensible to multiple such wafers to increase the emulation capability and add more systems. The way that you can partition problems, they can be run somewhat in parallel. And it's very different from what you see from the cloud computing, where you have outscale computations, when you have a large number of very small jobs that you can put on the cloud. So here you have a very large internal working set, very tightly coupled computation with very high external I/O bandwidth and very short latency. So there is really the only way to do that is to provide custom wafer scale solution to be able to address all those considerations, because nothing else meets all those objectives of high bandwidth, where we are pushing over 100 terabits per second on around one wafer, and short latency on the order of a few microseconds, short compute latency, and very large amount of signal processing inside.
That does sound quite challenging. Just being able to provide the power to each one of those chiplets. Now, is that right now CMOS chiplets upon a CMOS interposer, or how is that?
Right. So right now it's a CMOS chiplets on a CMOS interposer. You have compute array fabric, and then we also have computation of geometry. When we emulate these radar systems, then scenarios change and evolve over time. And you can almost think of it as a very high frame rate graphics that you need to really understand the scenario updates at a very fast rate. And then you need to be able to receive high frequency data at a few gigasamples per second and produce output at very high rate, sample rate, within very short compute time in between. And so from the power perspective, we take power delivery units that we take underneath the wafer and kind of vertically extend that in many slices to provide about 40-50 kilowatts for one wafer. And then on top of that, we have cold plates for flash cooling to take the heat out, where we are talking about 40 kilowatts in something that can be packed in equivalent 8U dimension for the rack. And it's about 10 times more power density than what you see in data centers, so it involves quite a bit of engineering to build adequate power subsystem, then to bring those power signals inside the wafer throughout the whole wafer, and then distribute clock as well, and run power and clock distribution across 40,000 square millimeters so that you can do reliable compute.
That is a challenge. And right now you're using a combination of commercial off-the-shelf tools and also some of your own in-house grown tools to do this.
Right. So right now we use standard digital flows for all of the chiplets. So that is on the order of 20 square millimeters in a 300 millimeter scale. You have about 2,000 of them. So we can synthesize individual chiplets, no problem. But when it comes to combining them together in a whole wafer scale, then we have a PDK for that packaging technology. So you have a few signaling layers on that packaging wafer, and you need to connect them all up. Even if it's just a simple parallel wires at about 10 micron pitch, several rows or columns of these, you still need to connect more than 2,000 instances. And routers, even though those are parallel wires, do not really like that kind of a job. So we are trying to write some internal scripts to work around those challenges, and we would appreciate to work more closely with your team to scale it up to the level of complexity at the full wafer scale that we can do this reliably.
Well, thank you, Leon. I appreciate your time and your insights.
My pleasure, thank you.